Before we actually begin the tuning process, there are a couple of small differences in the way we approach configuring our base fuel and ignition tables in order to perform our tuning on the road. We're going to deal with these now. First of all, we're going to look at the fuel table. So when we're tuning on the dyno, what we do is start with a completely flat fuel table, and we're going to simply have a flat table that gives us the correct air fuel ratio or lambda number in our idle area, and then we can begin building up the shape of our fuel table from there. This isn't going to work that well on the road because as we begin trying to drive the car, by necessity we need to move further through the RPM range than what we do on the dyno. And of course, with a flat fuel table, we're going to end up with very lean air fuel ratios as we move away from our idle area. Really, that fuel table is only going to be correct in the idle area of our map. So what we're going to do with our fuel table, once we've got our engine initially running and we know that our air fuel ratio in the idle area is correct, we're going to start building some shape into our fuel table. And all this is going to do is make a guesstimate at the sort of numbers that we might end up seeing in our fuel table. So let's have a look at how we can do that now. So here we've got our main fuel table, and you can see that we've got our engine currently running, and it's sitting at around about 800 RPM, and we're sitting at around about minus 70 kPa. So this is the idle area. We can see by our measured lambda value here that we're pretty close at the moment to our target, but we can see, as I've discussed, that our fuel table is filled with exactly the same number right through the entire table. So what we're going to do is make some changes to this table now. We're going to make this in two ways. First of all, we're going to deal with changing the values in the fuel table as we change the load or manifold gauge pressure, and then we're going to look at doing exactly the same in regards to engine RPM. So what we want to do is use our idle area, in this case about minus 70 kPa, as our reference point. So anytime we're below minus 70 kPa, we've got less manifold pressure, we've got less load on the engine, less air is entering the engine. We know that we're likely to need less fuel. So what we can do is simply reduce the numbers in our fuel table to represent that. And all I'm going to do at the moment is make a guesstimate of around about 2% per 10 kPa. So you can see I've made that change there to the minus 80 kPa row. I'm going to now copy that into the minus 100 kPa row, and we're going to make exactly the same change there, same magnitude of change. And we're going to do the same as we increase the load, so as our manifold pressure moves towards atmospheric pressure, a 0 kPa gauge or 100 kPa absolute. So again, we're just going to make a 2% change per 10 kPa, and we don't need to be particularly accurate here. All we're doing is making a guess that's hopefully going to get us a little bit closer to the correct operating air fuel ratios as we start tuning. And of course, it's going to be very easy for us to correct any errors we find in this table once we actually start running the engine, but this should at least give us a table that's a little bit closer to correct than if we have a flat table. Okay, so we've now put some shape into our fuel table in relationship to manifold pressure or engine load, and if we view the table visually, we can see that we do have a proper shape to that in one plane only. Now what we're going to do is exactly the same process. This time we're going to do this with regard to engine RPM. And what we need to consider here is what we're trying to achieve. We're trying to match the fuel delivery to the airflow, and you'll remember that the airflow really is represented by the engine's torque curve. So what we should see in a properly tuned engine is a fuel table or VE table that fairly accurately replicates the engine's torque curve. So we're going to see maximum numbers in our fuel table around about peak torque, At lower RPM, below peak torque, those numbers are going to be lower, and again as we move past peak torque and the RPM increases, we're also going to decrease the numbers in our fuel table. So what I'm going to do now is just simply take a guess that we're going to see peak torque somewhere around about 4.5 to 5,000 RPM, and I'm simply going to highlight those two columns and add 2% to both of them. Now what I'm going to do is highlight all the way from 4,000 through to 5,500, and I'm going to do the same again, adding 2%, and I'm simply going to copy this process through until we get down to our idle areas where we know that we're approximately right. So we're now down to 2,500 RPM, and I'm going to go all the way to 6,500 RPM. We'll do 2,000 RPM through to 7,000 RPM, 1750, and again I'll just copy this all the way through to 7,000 RPM, and finally we've got our 1,500 RPM and our 1,250 RPM column. Now again, we don't need to worry about being absolutely accurate at this point. All we're trying to do is get some numbers into this table that are going to allow us to get the engine running a little bit better than if we had a completely flat table of numbers. That's simply not going to work very well for us on the road. Now if I increase the throttle, we can see that as we move through this table, our air fuel ratio, our lambda values aren't correct, but they're much closer than if we'd simply had a single value. This is going to allow us to get the engine running so we can start our tuning process. And if we look at this table again graphically, we're going to be able to see, while it's not particularly pretty, we've got something that should closely or approximately represent the engine's actual fuel table shape. Okay, so now that we've dealt with our fuel table, we can talk about our ignition table. And in the dyno section of the course, we start with, again, a flat ignition table that's safe and retarded well below MBT, so it's not going to be likely to result in knock. In the dyno tuning section, if we're tuning on the dyno, we would then go through and optimize each cell of our ignition table in steady state to MBT. Now on the road, because we don't have the feedback from the dyno, we don't know how the torque is varying as we alter our ignition timing. It's not possible to do that, and this is really one of the big drawbacks of tuning on the road without the feedback from the dyno. So rather than starting with a completely flat ignition table, what we want to do is start with an ignition table that's going to be hopefully a good approximation of what the engine actually is going to want to see. Now the way I do this is come from years of experience tuning engines on a dyno and seeing what different types of engines want to see in the way of ignition timing, as well as analysing factory OE ignition timing maps. And I've provided base timing maps that should be a good starting point for both naturally aspirated and turbocharged engines in this course for you to get up and running. Let's have a look at the ignition timing that we've put into our VQ35 here as an example. So what we can see here is that in the idle areas of our ignition map, we're sitting at around about 15 degrees. At high RPM and low load, you can see that we're sitting at around about 35 degrees of ignition advance. In the typical area that the engine's going to be cruising and spending a lot of its time, we're seeing ignition advance values around about 30 to 33 degrees. And then you can see at high load and low RPM, I've got 10 degrees in there. And then as we move higher in the RPM, we are at 25 degrees. So this is the base table that we're going to start our tuning process with, and in the following steps we're going to see how we can optimize this table further without the benefit of the dyno. Our base fuel and ignition tables are now set up and we're ready to continue our tuning process.